So you are basically given a matrix called grid with the height of m and then n, which is the width. And then what we're trying to return is to return an array of row indexes, which is a good substring that is sorted in ascending order. So a good subset of rows is that if there is k rows inside your subset and the sum of each column is at most floor of the k divided by 2. So that's a bit abstract. Let's take a look at this for example. So given this matrix here, so the answer is 0, 1. So let's see what this matrix looks like first. If we draw out the input, it looks something like this. 0, 0, 0, 1, and then 1, 1, 1. So that basically the input. And then it says 0, 1. So basically we are choosing this particular subset of rows as the answer. As you can see, if I just make this as a separate matrix, in this particular submatrix, the k is 2 and k divided by 2 and floor is 1. So that's why we should have at most 1 in each column. So the first column is fine, it has no 1, so it's 0. So it's good, and this is good as well. You return it, so it's good as well, and you just continue, and it's good as well. Then it seems like everything is good, so that's why we're returning 0 and 1. I mean, there could be another answer for this, but in this input, I think there's only one answer. So we have to output this 0 and 1. But if there's multiple good subset, then we can just return any of them. And also another thing to note is that we can just return any of them, but not the maximum of them or the minimum of them. It doesn't matter. So there could be an answer, there could be only one row. So for example, this is one possible answer, and this could be 0, 1, 0, and this. So this could be an answer, and this can be an answer as well. So it doesn't matter which one we choose. So in this particular input that I just created, the answer can be 0, which means the first row, or it can be just 1 and 2, which means the second row and the third row. That's pretty much all to the problem description, and let's see how can we solve it. To solve this problem, there are like 2 main observations / ideas that you have to make or you have to observe. First is that when you notice in the constraint, the width of the matrix is always less than or equal 5, which is a big hint to us that we can do something about this. And the second thing is that when you take a closer look to the subset of the matrix, you can play around a bit with the example and you will realize that any size of k greater than 2 is quote-unquote meaningless. By meaningless, I mean if there exists a solution, and there must exist a size of k equals 2. So let's take a look at the example to illustrate the idea more. You can see the answer is 0, 1, which basically means just for this first 2 rows, which makes sense. But if you take a closer look, this can also be another answer of it, because this column has 1, and this column has 1, and this column has 1, this column has 1. This is also valid. So what I'm trying to say is that this thing is kind of unnecessary to include. And based on the constraint of the problem, let's say there is a subset of the answer. Let's assume there is 1, 0, 1, 1, 0, 1. Sorry, 1, 1, 0, 1 like this. And then there should be more things of this. Let's say this is one of the answer. This is the answer. So based on the constraint of the problem, we will know that if this one appears in here, it means there must be another row under here, somewhere inside the subset, that the first bit is 0, so that it can kind of cancel this thing out, basically. Similar for this thing, we need another row for it to cancel it. It doesn't really make sense to have two different rows to cancel things for us. Let's say something like this, we need 2 rows to cancel for us, so there should be a subset of size 3 instead of the subset of size 2. So we need to cancel this one. So therefore this will be 0, and this is 0 as well. And this, we can cancel that, but we don't cancel this. And we just keep doing this. And then we don't cancel this. Let's say if we combine these 2 rows, there's not enough for us to give an answer, because this one is still not in a good shape, so to speak. Therefore, it means if there's a valid answer like this, it means in the remaining rows, one of these must have this cancel out. If there is something that cannot cancel by this row, but it can be canceled by another row like this. So this can be canceled by another row like this. So this can be, let's say this one cannot be canceled by this thing. So that's the whole reason why we need another row for this. And let's say this one, when we take a closer look, then why don't we just use this row instead? Because we kind of need 2 rows to cancel this thing. If we need 2 rows to cancel this thing, then why don't we just choose that 2 rows instead? And we just cancel this thing. The similar logic can be applied to any row that needs 2 or more rows to support it. So by support it, I mean there is no direct complement to it. So what I'm trying to say is that, so this thing will be a direct complement to it. So basically we do an AND operator, and this will become 0. So that's what I'm trying to say by complement. So if this row or any row in that answer requires 2 more rows for a complement, then we can just remove this row and just leave the remaining rows. So this logic can be applied to every single row in the subset. That's why the final answer will always be just 2. I hope that's not too confusing. But once we have convinced ourselves that the answer will always have a k of 2, then the second observation is that the width of the matrix is less than or equal 5. So it means the pattern of the bit will be less than or equal to 2 to the power of 5, because there could be 0, 0, 0, 1, there could be 0, 1, 0, 0. So basically it's like a bit, but now we have 5 sides of this bit. So 5 sides of bit is 2 to the power of 5, which is 32. So 32 is a very small numbers. So that's why we can just combine these 2 findings. First, we know for sure that there should be if an answer exists, then previous row j, let's say j, and row I equals must exist for some I. So how do we check the previous row j? We cannot do n squared algorithm because the number of rows is really big. It's like 10 to the power 4. But now it's time for us to use the first observation, which is that the pattern of that is only 2 to the power 5. So basically, we will just loop through every pattern from 0, 0, 0 to 1, 1, 1, 1, 1. If this pattern exists or appeared before, and this pattern, I'm doing an operator here, and current is equals to 0, it means this is a potential answer. Then we just return the previous index first and then current index. So in this way, we do not have to kind of visiting all the row that we have visited. Instead, we just visit the pattern, and the pattern, as we said, will at most be 2 to the power 5. So that's why we can achieve something like 10 to the power 4 times 32, which is totally within the time limit. So in terms of O, so the time complexity will be OH, where H is the height of the matrix times 2 to the power of W. This will be our total time complexity. So it seems this is big, but you have to know that this W is less than or equals to 5. So basically, we can treat it as constant. Mean time come from here because this thing can be 10 to the power of 4. So that's basically the jigs of the solution and the complexity for it. And let's jump into the code implementation. So first we're going to initialize H as the height of the grid and then W as the width of the grid. And then we have to initialize the index of pattern where the key is the pattern and the value is the index that it appeared before. Then we're going to iterate every row index. Basically in here, we're just going to convert the row into a binary number and put inside into the variable num. So if the num is 0, it means that itself can be a good subset of matrix. So we're just going to return that. If it is not, then we're going to iterate every possible pattern. There's going to be 2 to the power of W of them. And then if this pattern and the current number basically apply the AND operation to them, and if the answer is 0, it means they could be an answer, and the pattern is also appeared before, and we will just return the index of the previous and the current index. Otherwise, we're just going to make a record of the current number that this pattern appeared in this row index. So later, the future row index will know. And then if nothing is fine, then we're just going to return an empty array as the answer. Let's try to run it. Accepted. That's pretty much all for this problem. Well, I think this problem is a little bit tricky, and it's not easy to come up with those observations like only size k is equal to matter. So I don't think this will be a very common interview problem, but anyway, it's a good practice, and I hope my explanation somehow help you, and I will see you next time. Bye bye.